This next section of dynamics kind of jumps into a hybrid of topics that all have to do with circular motion. So we're going to talk about circular motion, which is kind of a kinematics thing. Then we're going to connect that to centripetal force, which is a dynamics thing. And then we're going to kind of bring that into space exploration as we get into orbits and things like that. And so we kind of have a mashup of three different topics that are all kind of interrelated. And they start with understanding circular motion. So centripetal force, first of all, is any force that causes an object to move in a circle. So you can think of that as, what if you're going around a curve in your car? The reason that you can actually turn in a circle, or the reason you can go around a curve, is because friction between your tires and the road allows you to continue turning, right? If there was no friction, so imagine a really, really icy curve, you turn your wheels and there's not enough friction for your wheels to cause you to turn in a circle, and so you just keep going straight right into the ditch. So in that case, the centripetal force would be friction. Okay, so it's any force, we already know of a lot of them, it's any force that's allowing circular motion to happen. The direction of centripetal force must always be perpendicular to velocity. Okay, so let's look at this just for a second here. Let's say you're traveling this way. In order to get you moving in a circle, so this is velocity, in order to get you moving in a circle, the force has to be pulling you this way. Okay, and a force that's pulling you that way will cause you to change direction like that. And then the force is going to be perpendicular again, which will cause you to move like that. Perpendicular force, like that, perpendicular force, etc. Okay, now obviously it's more gradual than the thing I just drew. It's not like you drive in small straight lines. It's a nice gradual curve because the centripetal force is always perpendicular to your motion. And finally, the direction is always to the center of the circle. So whenever you're answering a question, you've calculated the centripetal force, the direction that you place on there will always be toward the center. Okay, unless you're talking about a specific position in a circle. So if you're going around a circle like this, and it's asking you what's the force right there at the top of the circle, the answer then would be down, because down is toward the center of the circle. Okay, but it's always toward the center. If we look at the example of a ball moving in a circle, the centripetal force is mostly accounted for by the tension in the rope. Right over here, the tension is downward, and that's the same as the centripetal force. Right over here, the centripetal force is upward. Now, if we would cut the rope right here, then the ball would fly off tangentially, and that's one way we know that the velocity of the ball at any given point is perpendicular to the centripetal force moving it in a circle. The centrifugal force, or centrifugal force, is not a real force. Centrifugal force, goodness, is the feeling you get when you are moving in a circle of being thrown to the outside of the circle. So if you can think of yourself, sure, let's go with in a car who's going around a curve really, really fast. If I'm going around the curve this way, I feel like I'm being thrown to the outside of the door, or I'm thrown to the door side of the vehicle. Okay? Or if you are in a spinning midway ride, you feel like you're being pressed against the wall as you go around. That's the centrifugal effect. It's not a force. It's a consequence of Newton's first law. It's your momentum. It's your inertia that's going that way. Your body wants to continue in a straight line, but there's something that's pulling you back into the circular motion. Okay, so the centrifugal force is not a force, it's just Newton's first law in action. So we have a formula here for the speed of an object moving in a circle. You may be familiar with it. It's distance divided by time. Now we are not calling this velocity, though sometimes I will just interchangeably call it velocity and speed, though velocity is not quite correct in this case. Because when you're moving in a circle, your direction is constantly changing. And so your velocity, you could tell me your velocity at a certain point, right there. It's that way. But you couldn't tell me your overall velocity because it would just be resetting over and over again, right? Because velocity has to take displacement into account and not distance. So we're going to be really looking for what's the speed of an object moving in a circle. Okay, so let's imagine going around a circle once. Going around a circle once gives you a distance of the circumference. Okay, the circumference of a circle is the distance around once, and the time to go around one circle, or the time to go around one circle has a specific term, and that's the period. Maybe you remember that from waves last year or last course. Okay, and our formula for the circumference of a circle is 2 pi r, or pi times diameter, whichever you'd like, divided by period, which is denoted with a t. So this is our formula for the speed of an object moving in a circle. We need to know the size of the circle, and we need to know how long it takes to go around the circle. So period is the time it takes to go around the circle once. That's usually in seconds. Frequency is just the reciprocal of that. It's the number of cycles per second. Okay? And so it turns out that the period is 1 over the frequency, and the frequency is 1 over the period. So cycles per second can also be written in its actual unit, which is hertz. And period is still measured in seconds, or seconds per cycle if you'd want to say it like that. Okay, and the last piece we need here for circular motion is a formula for centripetal acceleration. Okay, and this has everything to do with the rate at which the angle is changing. Okay, so let's look at a circle over here. Here's the center of the circle. Here is where you started. And as you move around the circle like this, your direction is changing. Okay, your speed maybe isn't changing. You're not speeding up or slowing down as you go around, but your direction is changing at a certain rate. Okay, this is the angle. Your direction changed by a certain number of degrees per second. And so that's what we're referring to with the centripetal acceleration. But I'm just going to give you the formula for it, and you can look up the derivation some other time so we don't have to use up time in this video for something like that. So the centripetal acceleration is equal to v squared over r. Okay, and the r over here is the radius of the circle, and that's in meters. And this v up here is the velocity, or speed. Ha! We should say speed. See? I told you I would interchange them. Okay. So your acceleration is the speed that you're traveling squared divided by the radius of the circle. So it has a lot to do with the size of the circle. Let's do one example. How long does it take an object to move in a circle once if it has an acceleration of 2 meters per second squared and the radius of its path is 3 meters? How long does it take to move in a circle once? That is period. It tells us its acceleration, so its centripetal acceleration is 2 meters per second squared. And the radius of its path, r, is 3 meters. So we're looking for period. It gives us acceleration and radius. So the period comes from the speed formula, 2 pi r over t, but we are not given speed. We are given acceleration and radius, and so we can start with the acceleration formula. Acceleration equals v squared over r. It gives us the acceleration, it gives us the radius, so we can solve for v. You could also rearrange this formula to get v by itself and then substitute that expression into the speed formula. That works just as well. And in fact, that would allow you to do no rounding in the middle. But for the sake of simplicity, we're going to walk through it this way. So v is equal to the square root of a sub c r. Okay, and again, like I said, you can plug this in here and then input the values, and that's totally fine. In fact, I'd be more impressed that way, because we all know that's what you're going for, right? So the square root of 2 meters per second squared times a radius of 3 meters. We don't need to do any conversions because everything is in the proper units. That gives you 2.449 meters per second. That's the speed going around the circle. So now we have that value for v, and so we're going to go 2.449 meters per second, or whatever the exact value is, equals 2 times pi times 3 meters divided by t. And so t is this 2 times pi times 3 meters divided by 2.449, or if you'd rather, square root of AR. And so our period turns out to be 7.7 seconds. Okay, that's the right number of sig figs from the question. They both have 2. That's our final answer.